This chapter will cover meta-analysis. A meta-analysis is a statistical technique that combines results of multiple quantitative studies. By pooling data, it provides a single, more precise estimate of an effect or an association. While it's a very powerful tool, it's not always appropriate. It might add precision to estimates, but the estimates can still be biased. So if you have a collection of biased studies and you combine them in a meta-analysis, you end up being more precisely wrong than you were before. It might not also be appropriate if the studies that you're trying to combine are too unlike each other. Maybe they're measuring different things, and so combining them doesn't really make sense. The two primary models used in meta-analysis are the fixed effect model and the random effect model. The fixed effect model assumes that all the studies that you are combining are estimating the same effect. This could be if you have drug A versus drug B, and you have 5 or 10 studies that have done RCTs testing those two, comparing those two together. Then they're trying to estimate the same effect. They will estimate the estimates will be a little bit different each study, but that's just down to sampling error. In a random effects model, you're assuming that each study is actually estimating its own effect. However, these effects are related to each other. It could, for instance, be a study of a behavioral intervention that's been tested against an active control in one study, a waiting list control in another study, a placebo control in another study, and so on. These are actually different effects that are being estimated, but they are related to one another. The random effects models is generally the one you should go for, as it accounts for both within study and between study variation. It's rare that you would find a situation where you have a set of studies that are all measuring the exact same effect or attempting to estimate the exact same effect. So the core idea of meta-analysis is to create a weighted average of the study results. So each study gets a weight, and it's proportional to or inverse proportional to the variance of the study's effect. What this means is that studies with smaller variance, i.e., more precision, get a larger weight. Practically, what that means is studies with small sample sizes get less weight, studies with big sample sizes get more weight. And then you combine the effects by weighting the average of the individual effects. So it's not just taking the mean of the effects, but it's taking the mean but giving every study a little bit of a different weight when creating that mean. There are many techniques that have been developed for conducting meta-analyses. You don't need to know about all the details. And in this course, we'll use statistical software to conduct the meta-analysis, which helps sort of with the details. You don't really need to know all the details if you're just applying the statistical code.